Alright gang, this video, Stat 1150, finding critical values. Focus a couple things. First of all, keep in mind that this procedure is when we're testing for a population mean. Okay? So, and when we do that, we conduct what's called a t-test. Now, we've got three types of t-test. We have one-tail test, which can come in form of an alternative where we're testing greater than, where our reject region is above. We can have a one-tail test where we're testing our rejection region is below. And guys, we can also have a two-tail test where we have rejection region above and below the value that's being tested in the null hypothesis. Now, you should know by now that this situation is when we have a mu greater than. This situation is when we have an alternative of mu less than. And this situation is when we have an alternative mu not equal to. Now, one of the things that's confusing to students when we start creating these critical values is what we do is we take our distribution. Now, in the previous problem, we looked at the weight loss for, I think it was subjects on the Atkins diet, and a dietitian had claimed that the average weight loss was 3 pounds. The first thing we do is we convert this to a t-distribution. And we have to remember that the t-distribution depends on what we call the degrees of freedom, which is n minus 1. The t-distribution has a mean of 0, and these values, these t-criticals that we get back over here, will be in terms of a t-critical. So these values, of course this will be a positive, this will be a negative, this is a negative, and this is a positive, because these values are found in the t-distribution where the mean is equal to 0. So it's awful confusing. I was watching a very, very, very good statistics professor teach last year, and he even made the mistake to draw the t-scores, the t-criticals in this distribution here, but it's not. This thing is converted to the t-distribution, and how is it converted? Well, it's converted by a z-score or a t-score, where we take the t, take the sample mean, minus the mean of the distribution, divided by the standard error. Okay, so that'll be illustrated a little later. Now, let's get our hands dirty and jump into finding some of these t-criticals. All right, so let's say that we are testing h sub o mu equal 25, h sub o or h sub a mu greater than 25. So we know that the distribution of sample means that the rejection region will be to the right because of the greater than. And the fail to reject region will be everything else. Now, We don't want to think about that in the relationship to mu equal 25. We want to look at that in the relationship of the t-distribution, which is mean equal to 0. Now this t-distribution is dependent upon the sample size. So let's assume that our sample size was n equal 35, which tells me that we have a degrees of freedom of 35 minus 1, which is 34. So what we're trying to do is we're trying to find the t-critical for the distribution that has degrees of freedom 34 that separates the reject and the fail to reject. Well, we also need something else. We need our alpha value. And let's just assume that in this situation our alpha value is 0.05. Well, guys, the area that pertains or represents the rejection region will always be our alpha. So our alpha is always equal to the area under the curve that represents our reject region. So guys, I know this area right here is 0.05. I know this area right here is 0.95. So how am I going to find this? Well, guys, I am going to use Stack Crunch. And I'm going to go to my calculator, and I'm going to go to the t-distribution, and I want this to be the standard. I want my degrees of freedom to be 34, and I want the area above to be 0.05. So the t-value, no, guys, I'm wrong on that. Shoot. The area above is going to be 0.05, so I need the t-value that creates that. So 1.69 is going to be the t-critical that divides this distribution into 5% above and 95% below. Okay? So my t-critical, shoot, I forgot what it was now. I was thinking about something else. Was 1.69. All right. Okay, let's work another one. The null. So we have this. What do we need to be able to work the problem? We need a sample size. Let's say the sample size is 100. So that tells me my degrees of freedom is 99. And I need an alpha level. Let's say it's 0.01. So from this information, I know that my distribution of sample means is going to be normal. Because I have not equal to, it tells me that I have a rejection region above and a rejection region below. So this is reject, this is reject, and this is fail to reject. So I'm going to have a t-critical that goes right here. T-critical is T star, that's the notation. And I know this is going to be a negative number. I'm going to have a t-critical right there. And I know this is going to be a positive number. because this is symmetric around 0, I know that the absolute value of both these numbers is going to be the same. If this is plus 2.5, that has to be negative 2.5. If this is negative 1.8, that has to be positive 1.8. So, next thing I know is I know that this area plus this area has to be 0.01. So this area right here has to be 0.01 divided by 2. And this area right here has to be 0.01 divided by 2. So this area has to be 0.005. This area here has to be 0.005. Why? Because my total rejection region has to be equal to my alpha value. Now, how am I going to find the value, the line in the sand that cuts this distribution into two parts? That part right there between the reject and fail to reject. Well, we use stack crunch. So I need the value that has 0.005 to the left of it with degrees of freedom 99. So I want the area to the left to be 0.005. And that value is negative 2.63. Now, what if I decided I wanted to do this part up here? Well, I could just do greater than 0.005, and I get 2.63, positive 2.63. So gang, the critical value would be plus or minus 2.63. Now typically you'll just report that as just the 2.63. The plus and the minus isn't reported. This is so much fun, we need to need to look at another one, right? Testing. All right, so we have H sub O mu equal 15. We're testing versus mu less than 15. Alpha value is 0.10. Sample size is 37. What's the distribution going to look like? Central limit theorem says the distribution sample means will be normally distributed. This is testing less than, so in the left tail we're going to set our rejection region. This part tells me that the total rejection region has to be 0.10. Therefore, this part over here is 0.90. Sample of size of 37 says we have degrees of freedom of 36. And because this is to the left of center, this right here is to the left of center, I know that my T critical is going to be a negative number. So I can do this one of two ways. I can find the area that the value that has 90% of the area to the right, or I can find it that has 10% of the area to the left, degrees of freedom 36 in both situations. Well guys, I'm going to do the area below. So I want the area below to be 0.10. And that is negative 1.31. Okay? Make sense? All right, let's put it to use. Critical value approach. Shoot, I didn't get the right one printed out. Did I use the critical value approach before? Huh. Guys, I'm losing my mind. I printed this out, the critical value. and I don't know what I've done with it. Well, let's just go on with it. Instead of p-value, let's do the critical value. And work the same problem that we did before. Okay, so guys, everything else is see previous. Same thing here, same thing here, same thing here. The difference is going to come when we work our problems. Let's see how this would work according to the critical value approach instead of the p-value approach. Well, it turns out that stating the alternative and the null and alternative hypothesis is the same. So as we saw in the previous video, the null was mu equal 3, the alternative was mu not equal to 3. Choose the significance level, that was 0.05, that was given to us in the problem as we talked about earlier. The test statistic, we're going to use a t-test, because we always will when we have a claim about a population mean. And the conditions were met because we had normality, we have independence, and we have randomness. Now, this changes a little bit. Part C, compute the test statistic and p-value. But instead of the p-value, what we're going to do is we're going to implement the critical value approach. So it starts with looking at the distribution of sample means. Since we have n equal 10, we know that we have degrees of freedom equal to 9. Since we're testing not equal to, it means we've got a rejection region in the left tail and in the right tail. And the sum of these two areas has to be 0.05. So the area in both tails, the area in this tail is 0.025, the area in that tail is 0.025. Let's go find these values. So the left is negative 2.26. And for reasons that I've talked about in previous videos, the right would have to be positive 2.26. So we could do it this way, greater than 0.025, because we want that in the upper tail. Compute, and you can see we get 2.26. So what I've done is I've identified the bounds, the line in the sand that separates the reject regions and the fail to reject region. Now let's see where our sample lies or falls. And we do that with what's called a test statistic. And in this case, it's called a t-statistic because we're using a t-test. The way you calculate a t-statistic is the way you calculate a z-score, a z-statistic. Sample mean minus the mean over the standard error. Well, guys, we saw earlier that the mean of our sample was 4.6. The mu is the claim in the null hypothesis. The standard deviation, I'm going to have to go get that because I don't remember it. Is 2.95, but guys, I don't know if you noticed or not, but look at this. When we did that, in columns, and we chose weight loss, look what we got down here. We got the standard error, which is exactly what we need. It's 0.93333333. Now, you might say, well, wait a minute, how do you know that? Well, let's calculate it and see if it's right. If I go the other way, if I just go stats, summary stats, columns, choose this, and just choose standard error, standard deviation, I'm going to get 2.9515. Well, if I take 2.9515, divided by the square root of 10, look what I get. I get exactly what I needed. Now, you might say, no, wait a minute, that had 3 forever, right? Well, guys, if I put this out forever, this 2.9515, and didn't round to 4 places, then I would get 9.33333 forever. But I rounded to 4 places, so I get some error out here at the end of the decimal. But nevertheless, I've got 0.9333. I go 5 places for technical accuracy. So I have 4.6 minus 3. Divided by 0.91234. My test statistic is 1.71, as we saw in the last video. Now, where does that fall? Remembering that we have a 0 right there, 1.71 falls about right there, right? It's between 0 and 2.26. So what region did it fall in? It wasn't big enough to fall in the reject region because I had to be 2.26 or higher to be out here, or I had to be negative 2.26 or lower to be down here. So it fell in this region right here, which is the fail to reject. So final decision is fail to reject H sub O. Now, you might be thinking, Dr. Darbro, the p-value approach is much, much, much easier than the critical value. And I agree with you completely. I would never, ever, ever do a problem like this unless it just required me to. And there are actually a couple of problems on my math lab, and I know I'm going to get bombarded with questions about that, and that's fine. There's going to be a couple of questions on my math lab assignment that require you to do the t-critical approach. But if you have the opportunity, use the p-value approach as I demonstrated in the previous video every single time. Guys, that's all I got. Take care.